mean, everyone. That's great. Oh, okay, Hannah's back. Fantastic. Oh, and she's gone again. So yes, hello everyone. Welcome to season 2 of the Future of Foraging seminar series. We're very excited to be kicking off our second season with Professor Nathaniel Daw. Just as a quick reintroduction, I'm Laura. Hannah is, I don't know if she's actually on screen right now. She's in Germany. Oh, and she's disappeared. Perfect time. She was absolutely fine up until we went live, and then now she's gone. But yes, so I am one of 4 co-organizers of the Future of Foraging seminar series. The others are around. Either they have tech problems at the moment, or they are not online, but they will join. Oh, here's Hannah. Hi, Hannah.
I'm sorry.
But we will be part of the panel discussion at the end. So just to give everyone an idea of the format for today, Nathaniel will give his talk, and then we will have a Q&A afterwards as part of also a panel discussion. So we will be talking with Nathaniel, but also if anybody wants to come on screen as well and ask questions, you'll be very welcome to, and you can message in the chat if you'd like to. So let me give a bit more of a formal introduction to Nathaniel Daw. I'm very pleased to introduce Nathaniel today. He's worked very extensively in the computational modeling of decision making, applying reinforcement learning principles to both behavior and physiology. So he completed his undergraduate studies in philosophy of science at Columbia, and then moved on to a PhD with Professor David Turetsky. And during his PhD, he worked on RL models of the dopamine system. He then joined the Gatsby at UCL as a Royal Society Research Fellow, and he published seminal work with Peter Dayan, Yale Niv, and others on understanding how different decision-making systems are distributed in the brain. He continued this work as an associate and then an assistant professor at New York University, again exploring novel applications of reinforcement learning in health and disease. And since 2015, his lab has been based at Princeton University. In 2019, he was given the distinguished position of Professor in Computational and Theoretical Neuroscience. So his lab now continues to work on the neural basis of decision-making and learning, applying Nathaniel's wealth of knowledge in the field to new problems and contexts, and all united by an underlying rigorous computational approach. So the talk he's giving today, I think, is a really good example of this, as he will be discussing the ubiquity of opportunity cost in foraging and in other contexts. So Nathaniel, if you'd like to share your screen. Thank you.
I will try.
Yes, there we go.
Okay. Okay, good. Well, thank you so much for inviting me. I'm very excited to be here and to talk to you all. I'd like to talk about a set of ideas that sort of center on the classic ideas from foraging, but hopefully show you how they go beyond that. So surely for this audience, I don't have to remind you of the sort of core idea, but I thought I would go through it just in case. So really, actually, in neuroscience in general, and my lab personally, kind of in my day job, mostly what we study is sort of not foraging, right? We study a different type of choice, which you might think of as choosing from a menu, right? So we give organisms a series of options, whether it's a list of choices they could choose between, or a sort of trial and error between 2 levers or 2 decks of cards or something, or even something like a game where there's lots of different possible moves. And of course, the goal here, as we sort of all know, is to evaluate the different individual options and compare them to one another so as to make a choice. And of course, this has been one of the main reasons I think foraging has become important in neuroscience is that this type of choice has been contrasted to another type of choice, which it is argued might have different neural specializations and might be kind of more common in the natural world. And that's, of course, choice not from a menu of simultaneously presented options, but choice from options that are presented serially. Where you sort of encounter them one at a time and you have to decide whether to accept or reject them. So of course, that's the kind of choice that faces the foraging animal who's, say, hunting, whether to go after the zebra or see if they can find something else that doesn't run as fast. But also in, I think, the rest of our lives, it comes up in employment decisions, like looking for a job or interviewing candidates. It comes up in mating decisions, where you often, again, you encounter prospects serially rather than all at the same time. And the sort of big question that raises and which foraging theory seeks to answer, is how do you evaluate options when you don't know what the alternatives are? How do you evaluate the alternatives to compare to the sort of current prospect when you have yet to sort of seek them out or encounter them? And the answer that the beautiful answer that sort of comes out of optimal foraging theory, which is what I sort of want to sort of chase down today, is that instead of evaluating the alternatives individually and comparing them, you sort of evaluate the universe of options in general. So you track something like environmental quality, and in particular, there's a lot of work using something like the average reward rate in the environment as some kind of a measure of that. Okay, so what I'd like to do today then is argue that that's actually um, a very ubiquitous kind of variable and sort of logic that comes up not just in the foraging context, but in lots of other contexts as well. And indeed, in my own work, I encountered it a bunch of times before I even learned about foraging. And I'll describe a few of those hopefully today. So I thought I'd start with some sort of classic work on foraging to lay groundwork, but then I want to point out how these ideas relate to stress and mood, other types of opportunity cost, like whether to behave more vigorously or more slothfully, whether to deliberate or act. Um, and then at the end, I thought I'd relate to another, even sort of more distant class of issues involving efficient coding of decision variables and sort of reference points and risky choice and so on. So again, my goal is to sort of try to convince you that this set of ideas goes way beyond the sort of classic foraging setting, and indeed way beyond sort of serial choice, and right back into sort of choice from a menu. Okay, so again, the classic foraging story, which goes back to Charnov and Stevens and Krebs and so on, is based on the idea of serial encounters, right? So there are two classic tasks which have slightly different settings or slightly different sort of events in them, but they have basically the same optimal solution. So there's this sort of patch leaving task, which is the idea that an animal might forage for food, that they encounter it in a series of sort of patches, like a pool full of fish or a tree full of berries. And their job is to sort of harvest where they are until the patch is depleted, and so the patch gets sort of worse and worse monotonically, and eventually, as the berries come less often, they should sort of search for a fresh patch, right? Which will take travel time and risk of predation and so on. And so the question is, how desperately should the animal forage the current patch before leaving to find another one? The Preelection task is sort of another variant of the same logic. This is meant to model a sort of hunting animal who spends his time searching. And once in a while, he encounters a rabbit or a zebra or a rat. And he has to decide whether to engage with and pursue that prey or forego it and find something else. So different prey have different rewards. Rats aren't that tasty, but they might be easier to chase down than a zebra. So there's some combination of a reward benefit and a time cost, and the animal has to decide which ones to accept. How desperate are you? Do you want to settle for a rat? Or to just leave it aside and go search for something else. And so it turns out that basically the optimal choice rule for both of these scenarios and many others looks like this. It says you should compare an option, either the sort of current reward rate on the patch or the reward rate associated with the prey you just encountered, to something. What is that something? It's a measure of how good the overall environment is, and that measure is known, I'm calling it R star. It's the long run average reward rate that you've observed in the environment so far. So the thing on the right, the sort of threshold for whether you should accept something or reject it, is a measure of how good, again, not any particular alternative is, but how good the environment is, right? And it turns out if you in these two situations, if you choose according to this rule, then you will actually maximize your long-term rate of reward by choosing things, of course, only if they're better, sort of in the net, better than expected. So this is in the patch leaving context, it's known as the marginal value theorem. So another interpretation of this average reward, which is closely related, is that it represents the opportunity cost of time. So you're going to spend some time harvesting the patch, or you're going to spend some time chasing down the rat, and it's only worth your while to do that if the net reward or the net sort of profitability that you achieve during that time exceeds, the opportunity cost, what you would have expected under the status quo to earn during that time. So if I were being, for some reason, giving this talk for free, I shouldn't have done it because I could also be, shoveling sidewalks for $20 an hour or something. It, it, and the concept is that optimally you should only accept options if they pay off on the net relative to the status quo. This in turn, this sort of choice rule, which is common basically across these two tasks, makes a key prediction, which is that the selectiveness of the organism, whether how desperately they forage before they leave, or how desperately they or pickily they accept various proffered prey, should fluctuate according to the overall environmental quality. So the type of experiment, I'll show you a couple that you can do, is manipulate various aspects of the environment that have the effect of turning R star up or down, making the world on average better or worse, and you should see changes in the choice behavior. This has been demonstrated lots and lots of times in field data and experiments and so on. I'll show you a couple human experiments that we've done that capture this idea. So here's one. This is work I did with Sarah Constantino. And we did this sort of patch foraging task in undergraduates. So people saw a picture of a tree on the screen, and they had to decide whether to stay or exit. If they stayed, they'd have to spend some time shaking the tree, and they won a certain number of apples, which would be turned into money at the end of the experiment. And if then they face the same decision again, and if they shook the tree again, they'd get fewer apples because it was depleting, and so on. If they exit, then they have to wait a longer time. That's the travel time, and slowly watch the tree scroll off the screen and a new tree scroll on the screen, and then they're back to the beginning again, but the tree's repleted. So super simple, sort of just a direct animated version of the classic patch foraging task in a discrete trial format. And then you can just layer this with a number of different predictions or a number of different manipulations that would affect the average reward, and see if the subject sort of threshold for leaving the tree changes, right? So for instance, we can change the travel time, right? So if we make it so that they have to wait longer between trees in a different block, then the average reward per harvest overall is going to go down, right? Because they're spending more time between trees, and that predicts that they should leave the tree, later compared to if there were a shorter travel time. A lot of these things you could sort of figure out, without the marginal value theorem. But the beautiful thing about the marginal value theorem is it shows how to sort of launder all these different manipulations through a single number to figure out what their effect should be on foraging behavior. So another environmental manipulation that we could do, and we did, is to change the depletion rate. So you could have the tree deplete faster, or the tree deplete slower. And if the tree depletes slower, then the world's richer. And actually that means that you should leave it sooner, that is, leave it at a less depleted state than you would have in the world where it depleted faster, and so therefore the average reward was lower. So people do amazingly well at this. I have to say, again, I spend most of my time studying a totally different class of tasks, and this is the one task I've seen where every single kind of NYU undergraduate, who aren't generally very willing participants, just nails it. It's like it's built into their brain or something. So here's an individual subject. Gray is the optimal behavior, and red or orange is an ABAB kind of manipulation of sort of raw behavior as we change the travel time back and forth from long to short. And what we see is the people do a pretty good job of adapting, quite rapidly to these changes in the contingencies. What's plotted is the threshold in terms of the apples at which they leave the tree, right? And you can see that indeed, when the travel time gets shorter, they become pickier. The threshold goes up. Here's another person in a depletion rate condition. In the steep condition where the world is worse, the threshold goes down now. And again, they forage more desperately. And again, they do a pretty good job adapting quite rapidly. And again, one of the reasons I say that this is one of the better tests I've ever tried to run with undergraduates is that I think every single person in this study, maybe there's one exception here, got adjusted in the correct direction with respect to, in the predicted direction with respect to the manipulation of environmental quality. It just seems very natural, and the data are very clean. There's a lot of individual variation, which we'll come back to a little bit, in the kind of overall threshold. So the optimal predictions are in gray, and there's lots of findings that in humans and other organisms that organisms tend to over-harvest of it. They leave a little later than they should on average, but you can see people vary a lot around that average. But all of them adjust, more or less all of them adjust in the right direction. So another aspect of this, which I'm actually not going to focus on today, is we put a lot, because we do learning again in my day job, we put a lot of effort into modeling this sort of trial by trial adjustment in the choices. And it is indeed kind of best explained in our hands by assuming they're just learning the opportunity cost. They're sort of maintaining a running average of rewards. And that's what's driving their sort of trial to trial patch leaving, or tree to tree patch leaving. We've done the same experiment, or Gary Kane and Gary Aston Jones have done the same experiment in rats. The data are plotted a little bit differently, but they're very similar. Both they respond in the correct direction to both manipulations. And of course, this has been done by lots of other people in lots of other circumstances. So again, an example of choice behavior that's sensitive to manipulation of the overall environmental quality as predicted. Let me give you one more example. This is now a pre-selection task, which we sort of gamified and studied on the internet with large groups of people. Here, you're flying in a rocket ship and you encounter one of 4 different kinds of aliens that take a different amount of time to capture, long or short, and give you a different amount of points, fuel reward, high or low if you do capture them. And what's manipulated across blocks between environments is that the world is either rich or poor, in the sense that the worst alien predominates or the best alien predominates. And the prediction is, when the best alien predominates, you should skip the middle aliens, and when the worst alien predominates, you should pursue the middle aliens. And that, so in a poor environment, you should be less selective. And that's actually what we see, although there's sort of an interesting wrinkle, which is that there's a big effect of block order. So we didn't actually expect this, but when you break the data down by whether they were in the poor environment first and then move to the rich environment, they do a pretty good job. This is the medium alien. The prediction is that they should always take the best alien and always skip the worst alien, but in the rich environment, they should avoid the medium aliens. And they do a pretty good job of adjusting as the world gets better, becoming more selective. But if you turn in the half the subjects who ran the other way, they significantly adjust up, but not nearly as much, right? It's a much sort of slower or less complete process. And if you let it go long enough, they sort of manage to, but you can see that there's clearly something asymmetric here about moving from a poor world to a rich world versus moving from a rich world to a poor world. Interestingly, in this task, for various reasons, it's easier to sort of visualize this in pre-selection than it is in patch foraging, but we can actually see evidence of adjustment of the threshold or sort of adjustment of quality or tracking of the average reward on a trial by trial basis. So if you just plot the chance that they accept any alien on trial T as a function of whether they saw the best one, the middle one, or the worst one on trial T minus one, you can see that they're a little more desperate if they just saw the worst alien, and they're a little pickier if they just saw the best alien. And so this, I think, you can really see that there's sort of ongoing learning of how selective you should be, like they're tracking the average reward rate. And again, we modeled the data. That's the type of model that did a good job of explaining the choices, the sort of trial by trial time series of accept and reject, with the added caveat that we needed sort of asymmetric learning rates with respect to sort of good and bad news to capture this asymmetry in the sort of global adjustment. Now I think that's actually interesting, and we talk about it a lot in the paper, because that's something that's been seen in a lot of other contexts and a lot of other learning tasks. So people call it an optimism bias, including my co-author Neil Garrett, and a number of other contexts. But seeing it pop up here is actually interesting, because in many situations, to choice from menu situations, it doesn't matter so much if you're more sensitive to good news than bad news, let's say, and that just biases all the alternatives to be optimistically evaluated, because they're all optimistic, and so you still sort of choose what you would choose. It doesn't make a great deal of difference. Here, because of the sort of nature of foraging, if you don't do a good job of tracking the opportunity cost, or if you're sort of pessimistic or optimistic about the overall environmental quality, then that really changes your choices, right? As you see here, they don't take the poor alien when they should, right? They don't take the medium alien when they should. And so this is actually a situation in which a sort of relatively common aspect of learning actually could have pretty big effects. One more thing to say about this, Neil Dundon did this experiment, actually these data are his version of it, with very extensive cardiac monitoring to try to study autonomic engagement, partly for reasons I'm going to discuss next. But oh, it didn't pop up. Well, I was going to show you that. Maybe it comes back later. All right. In any case, I guess that's why this is, because I was going to introduce that point. So what I've shown you so far is the sort of traditional story told in humans, that the average reward standing in for the opportunity cost or the environmental quality modulates people's sort of selectivity or pickiness or desperation in these foraging tasks, right? So behavior across different tasks and actually different species modulates with environmental quality in the way that we think, and we can even see that happening sort of trial by trial. So that, of course, raises a question about the mechanism, right? What is going on in the brain to track this? Now, I actually have a bunch of different hypotheses about this and some evidence for some of them. And I don't think it's a single thing. Like I'm going to speak about these as they're all the same, but clearly not all the same. But I think they share a sort of common logic. And that logic is, we have a bunch of systems in the brain, or a number of them, that are really about sort of monitoring the environment in some way or another and coordinating in kind of a big picture way how the body and the behavior respond to it. So the autonomic nervous system, right, is an example of that. And stress. It's tracking some aspects, you know, globally of the environment that you're in. You're in danger. Is it rich? Is it poor? And it's deploying a whole range of sort of responses to that, whether it's fight and flight or, you know, respiration and different things. So that's one system that seems tailor-made for keeping track of sort of environmental quality. And another is kind of emotion and mood. And to some extent, you could almost say the same thing, right? What's emotion? Emotion is, you know, roughly speaking, how your brain evaluates either the sort of overall situation or individual context, and again, kind of deploys a range of appropriate responses. If you're angry, you get aggressive, and you have appropriate facial expressions, and you have appropriate heart rate, and it's a package of responses, right? So I think that's another system or sort of a way of thinking about how the brain might be sort of implementing this type of tracking of the environmental quality. There's one more thing, which is that we have systems, of course, in the brain that are very interested in tracking rewards, right? In particular, dopamine. Dopamine is interesting because it sort of famously responds to sort of individual rewards or stimuli predictive of rewards um, with sort of fast transient responses, but dopamine also has a lot of kind of overflow, and a lot of its signaling is through sort of volumetric propagation and extrasynaptic propagation, extrasynaptic receptors uh, in the sort of CSF and striatum. So there's a sort of volumetric kind of slow timescale aspect to dopamine. Um, and that is probably tracking the reward level, or sort of uh, effectively modulating the reward level at a kind of longer time scale basis. And we think that might be, again, one uh, system in the brain that might drive some of this foraging behavior. Okay, so how can we test this? Before that, one thing that's kind of interesting about all of these, which kind of relates to the theme of this talk, is that every one of these things, whether it's stress or mood or dopamine, um, what they have in common, in a sense, is that they do a lot of different things, right? They don't just do foraging. I sort of stressed when I was talking about stress and mood and the autonomic nervous system, that each one of them coordinates a whole range of responses, and among those things might be foraging, but there might be other things as well. Dopamine is also sort of famously involved in both reward and length rewards, but also movement and vigor, and so again, I think it's got a sort of multifarious set of associations. And I think actually, as I'll come back to this, these foraging ideas help us kind of understand that and think about that diversity. Indeed, I'm just going to go ahead and say this, but originally when I imagined this talk, and if you read the abstract, I sort of imagined I'd go through each of these things and tell you about them, but there's sort of not time for that. So I'll unpack a few of these examples a little bit more later, but um, for now, I just want to say that this sort of logic of opportunity cost, and even the sort of decision variable R star that we saw coming up in the foraging examples, has actually been extended to lots and lots of other situations. Um, Pretty much any situation you can think of that turns on trading the cost of time against some benefits from delay. So I'll talk about whether it's worth moving vigorously and spending energy versus moving slowly. Our star turns out to be the thing that tells you whether you should do that, for the same reason it tells you whether you should leave a patch. Alex Kochelnik talked about intertemporal choice this way. Speed accuracy trade-offs can be conceptualized this way. We and others have thought a lot about deliberation and when it's worth deliberating versus just going ahead and acting. That also turns on how much the cost of deliberation is, which is our star. Similar with exploration versus exploitation. A lot of work in perceptual decision making involves a sort of similar thing where you can spend time gathering information, or you can just go ahead and tell the experimenter which way you think the dots are moving, and on and on. So these are really all the same model applied to kind of different behaviors, or even what I would call sort of meta behaviors, like adjusting how you do behaviors, adjusting your own decisions, or something like how much to deliberate. And they, if you sort of write down how should you do this, you end up with our star again, for pretty much the same reason it shows up in foraging. And depending on the particular, which of these bullet points we're talking about, there is or isn't evidence that this is actually how it works in the brain. But it's sort of striking when you look around how many places this pops up. Oh, okay. So let's come back then to stress. So we tried to test the idea that stress might be sort of one of the brain's mechanisms for monitoring environmental, quality and guiding patch foraging decisions or foraging decisions by doing this sort of apple task, in undergraduates, but now with both a sort of a stress questionnaire about how many chronic stress events have you experienced in the last month, how many times did a spouse leave you, how many times did someone die, um, and also with a acute stress manipulation, the sort of arm and ice water cold pressor manipulation. So this is work by Jennifer Lenau and Liz Phelps, and the bottom line is that you might expect that as you increase stress, either exogenous stress before they walk into the lab, or uh, endogenous stress or experimenter induced stress through this acute stress manipulation, which we measure its efficacy through measuring salivary cortisol. What you see is, on average, people in our patch foraging task forage more desperately. These lines slope downward. You can see that here. This is sort of a low stress subject. He forages less desperately than optimal. This is a high stress subject. He or she forages more desperately than optimal. And so this is sort of, I think, consistent with and it's even kind of causal manipulation, right? Consistent with the idea that the autonomic stress response, one of its effects is to deploy, is to guide this type of judgments about the quality of the environment for the purpose of guiding foraging decisions. I think it's also interesting to think about, there's lots of work on stress and decision making. For instance, it's thought to reduce deliberation and so on. It's interesting to think about to what extent this opportunity cost idea could actually help to explain a larger range of them, and that's a sort of issue for future modeling and actual work, and something we had a lot of discussion with the viewers of this paper about. And here's the thing I was expecting to pop up before. You could even see this kind of heartbeat by heartbeat in Neil Dundon's study. So they measure something called PEB, pre-ejection interval or something. I'm sorry, I can't immediately think of the acronym, but it's a rapid measure of the mobilization of the sympathetic nervous system, and it actually turns out, and if you think about it, it's sort of parallel to this experiment, the more sympathetic autonomic mobilization you have across subjects, the better you are at this thing that seems to be hard for people, of moving from rich to poor. There's sort of a selective effect where if your heart is reflecting this a sympathetic mobilization, then you are better at moving from the rich environment to the poor environment, adjusting your behavior and becoming less picky as you should. So it seems like this stress response is even involved in the behavior, or autonomic response is even involved in the behavior at a very sort of granular time scale. Here's another piece of work, and this is now an old piece of work that I worked on with Yael Niv and Peter Dayan. We were interested in tonic dopamine, or even dopamine, really. And the question that we sort of had faced was, at the time, everyone was very excited about these reward prediction error models of dopamine. So Wolfram Schultz and so on had shown that the neuromodulator dopamine, or neurons that contain it, respond to rewards, and they respond as though it's a so-called reward prediction error. The difference between the rewards you expect and the rewards you got. This was thought to be involved, is thought to be involved in learning from rewards. But what was kind of clear at the time, and is still kind of a puzzle, I think, is that dopamine is not just involved in learning, right? It's somehow involved in movement and performance. And much of the causal evidence, such as things like Parkinson's disease in humans, which is a degenerative disorder that affects, that depletes dopamine, and the effects of drugs like cocaine and so on, which release dopamine or agonize dopamine, or both, it have the effect, perhaps not just of driving perhaps reward learning or making you repeat actions or something, but also just causing you to act more vigorously, or the lack of dopamine making you almost paralyzed, right? So dopamine seems to not be just involved in signaling rewards for learning per se, but also somehow in invigorating energetic behavior. So we tried to write down a sort of first principle model of how should the brain decide not just what to choose, but when you choose an action like pressing a lever, how fast should you do it? How vigorously should you do it? Assuming that doing it more quickly incurs greater energetic costs, right? And doing it more slowly or slothfully incurs lesser energetic costs. And what you basically arrive at is, again, the marginal value theorem, that as the average reward per time step goes up, this R star, it comes up again here, then all else equal, you should lever press faster because the cost of sloth in units of R star is going up, right? So that suggests that the average reward should be related to not just to patch leaving, but also to operant vigor, or vigor of all kinds. And then the other suggestion of this work was perhaps this sort of extracellular dopamine we're talking about, which sometimes people call tonic dopamine, although that's a bit of an ambiguous uh, phrase. If the concentrations of dopamine that are sort of diffusing through striatum and extracellular fluid, perhaps those actually track this average reward. And then if so, they could sort of modulate the famous direct and indirect pathways in the striatum and sort of directly causally control vigor. And it turns out in these reward prediction error models, you basically get this for free because the average reward is also the running average of the phasic reward prediction error signal that the dopamine neurons appear to in their fast phasic signaling to signal. And so if you just sort of let that spill out in the extracellular fluid and clean it up slowly, you get the time average of that hanging around the extracellular fluid. And it is what you need to track R star and guide, among other things, operant vigor. And therefore, this also aims to unify these two different aspects of dopaminergic signaling, the activational or vigor-inducing part and the reward learning part, through a sort of single, more complicated model. So I think this idea was pretty speculative at the time, but has held up pretty well. So for instance, this is data from Josh Burke's lab from Ali Mohibi. And this is showing that the reward rate in I forget if it's mice or rats, to be honest, doing a sort of bandit operant decision task, tracks the latency of their trial. So this is black is the reward rate, and that relates to latency. So that's sort of half the theory that the animals go faster when they're winning more rewards, as we would expect. And it's also the case that if you just using the, and this is what Ali did, if you use the dopamine fluorescent molecule D-light to monitor sort of dopamine, and we're looking specifically here, what Rick Naogi did is plot the sort of background rate of dopamine just before a trial starts, not filtered or anything. Just so what's dopamine doing when it's not responding to something? It really does track the reward rate, so that when rewards are dense, it's high, and when rewards are thin, it's low. So you put these two things together, and these are sort of the two elements of the NIV model. Now, I'm not going to. So Josh Burke, who's also my collaborator and good friend, has a different interpretation, particularly the fast time scale dynamics here, and there's a long discussion to be had about that. And I'm not going to go into that aspect of it today, but we, having looked at this data, Rick in particular, and thought about it a lot, we think that this is actually right in line with what the NIV model predicted, and we think this is pretty good confirmation of this idea that dopamine is tracking the opportunity cost of time, and that's driving changes in vigor. Okay. Oh, and it is also the case then that dopamine also has causal effects on patch foraging tasks. Sarah has shown that in my lab, and a group at Oxford has also shown that. So again, tying together the same decision variable seems to be affecting different aspects of behavior, both operant vigor and how desperately you leave a patch. These are causal manipulations involving Parkinson's disease and medications and so on in humans. Okay, let's talk a little bit about mood. I don't have any results to show here, but I think it's a useful thing to think about. So what's emotion, right? Again, emotion is another of these systems that you can think of that the brain uses to evaluate situations and release a set of coordinated responses, right? And one important distinction is between, often made by psychologists, between a feeling, which is like what happens in response, transiently to some particular event, like someone says something mean to you, versus a mood, which is kind of a lingering, kind of global evaluation that isn't might be triggered by something, but sort of lasts a long time and isn't particularly tied to an individual event. I think this is an interesting distinction because people in decision neuroscience have thought a lot about relating the types of decision variables we use in sort of choice from a menu problems, that are evaluations of particular events or particular options, to feelings, but there's not an obvious kind of computational counterpart to moods, but there is, right? And that's, of course, our good friend, the average reward, right? These sort of environmental evaluations we can think of as being they're sort of long run, slowly changing evaluations of the overall sort of global situation. That's kind of what a mood is, right? And so we sort of, identify maybe another aspect of this sort of average reward idea with mood. One of the reasons that's interesting is, of course, in thinking about disorders of mood. So I think one of the sort of sad or unfortunate things about mental illness, um, and where we are scientifically in trying to understand it, is that all of these disorders are syndromes, right? So if you look in the DSM-5, what does a mood disorder look like? It says you have to have 5 of the following symptoms. There's like a sort of random list of things that nonetheless seem to come together: depressed mood most of the day, significant weight loss, insomnia or hypersomnia, psychomotor agitation, fatigue, right? And what we don't have is what doctors call an etiology. Like, why are you coughing and have a fever? Because a virus, you have COVID, and COVID gives you all these different symptoms. We don't know that for depressive disorder, right? It just like lists the things you have, and if you have 5 of them, you have depressive disorder. Like, why is that? And one thing to note is you have these sort of more sort of cognitive or sort of subjective kind of symptoms like depressed mood and feelings of worthlessness, and then you have these more kind of energetic or motoric symptoms like psychomotor retardation or agitation, weirdly, fatigue or loss of energy. Um, uh, and so there's sort of 2 sort of behavioral aspects or energetic aspects, and again, sort of evaluative aspects that go together. And kind of for the same reason as for dopamine, we think, and this was work with Peter Dan and Quentin Huyss, we argued that our friend, the average reward rate, might actually kind of tie a bunch of these things together and give us a sort of candidate for a sort of underlying cause that gives rise to this sort of spectrum of symptoms. So in particular, mood and sort of the anhedonic aspects, as I've been saying, relate to perhaps evaluation of average reward, but these energia kind of symptoms, fatigue and loss of energy and retardation, also do, for the same reason they do in the Niv vigor model, right? Like if the average reward is lower, then it's less worth spending energy to act quickly. And so, this so far is a prediction. This might be a way of sort of thinking about underlying causes of the disorder or aspects of the disorder. A bunch of groups are actually trying to look in these foraging tasks at effects of major depressive disorder. The prediction is, of course, that a lot like stress, that people with depression will forage more desperately due to having a sort of suppressed average reward representation. I don't have anything to show you on that. I've heard good news from various people. I think we might be seeing something soon. So I think that's a sort of exciting direction. Okay, now I want to change gears. I want to go back to choice from a menu. Okay, so I've been talking about a bunch of different tasks that involve, one way or another, trading off time versus sort of cost of time versus rewards due to spending that time. But I want to come back to the types of tasks that we often study in my lab and others, and argue that we can see a whole different set of effects involving average rewards or similar things in this context as well. And this now is quite distinct. It's not really about intertemporal choice, but I think it's another aspect of why the brain cares about tracking reward averages. So this is one of my favorite studies. It's not mine. It's from Stefano Palminteri some years ago. And what he did was he trained people to choose between two different slot machines by trial and error. And there are two different contexts, actually 4 slot machines. One, the good one, pays off by giving you a gain. You have a larger gain for one of them on average than the other, which is realized noisily by winning $1 or winning nothing a quarter of the time or 3/4 of the time. And then there's a sort of mirror image thing in the loss context where you could lose money, but you would lose less or less often if you chose the better one. So people could learn both these things. They could learn them about equally well. And then what he did with this sort of clever manipulation was give you a transfer test where you were asked to choose between different pairs of slot machines that hadn't been trained together. And the key test in his hands, or that he was interested in, was comparing the better slot machine from the worst context against the worst slot machine from the better context. So the worst slot machine from the better context is objectively better than the other because it involves a small chance of win. But during the learning context, it was relatively worse than the other. And it turns out that people have a tendency in these kind of transfer probes in some conditions and so on to choose the objectively worse slot machine because it was presumably because it was the contextually better one when you learned about it. So this is another kind of context-sensitive effect, but it's not a context-sensitive effect so much on choice directly as on learning, right? Like people are learning about the value of slot machine B and slot machine C, and the model that is, if you look in the supplemental material, the Palminteri paper, is that they're learning from the nominal reward, the received reward, minus R star again. So here's our friend R star, and now it's being used not to directly compare rewards at the time of choice, but to compare rewards to sort of net out the average reward as you're learning how good an option is. And so therefore R minus R star is sort of positive for C but negative for B, and that leads to this inversion. So here it is again. Now there's a question of why the brain does this, and that was the last thing I wanted to talk about, connecting it to another set of work on that. I think one way to think about it is to connect it to a bunch of other work on choice from menus involving basically efficient coding of decision variables in the brain. So let me say a few things about this. And I should say that this last sort of line of work I'm talking about is really most strongly associated with Paul Glimcher and Kenway Louie in his lab, who pursued this idea in a number of different ways. It's not something I've actually worked on. So what do I mean by efficient coding of a decision variable? So here's what I mean. This is a classic idea going back to Barlow and so on in perceptual neuroscience. The observation is, of course, your brain spends a huge amount of your energy basically firing electrical spikes, right, to represent whatever it represents. So something like 20% of the food that you take in every day, 400 calories or so, more if you overeat like I do, it goes to driving your brain. So the spikes that neurons use to communicate with are metabolically costly. And so for this reason, we don't have unlimited firing rates, and we don't have sort of, in part for this reason, we don't have unlimited precision in the things we represent in our brain, right? So you can think of it as though representing quantities such as perceptual quantities in your brain, the information is quantized by some almost like bins, right? The number of spikes that you have to work with. This implies that you need to code whatever it is you're trying to code efficiently. So for instance, you've got to mean correct the center, the distribution so that you don't fire lots of spikes for a sort of average response. You want to sort of have set the distribution of bins representing different firing rates to different stimuli in the world to reflect the natural statistics. And the brain does a really good job of both kind of shifting and scaling. This is a lot of perception. Um, our representation of uh, quantities, and perceptual quantities mostly been studied as, so as to sort of put the most coding, the smallest bins and the bins that are sort of most intermediate, and the most precision into the most common stimuli, right? Like the ones that live in the middle, for instance. So if the distribution of brightnesses in the world, during the day is this, then you need this sort of gain on your, retinal neurons and V1 neurons and so on. And this has been famously studied. So this, for instance, is data on fly retinal neurons and their contrast sensitivity, showing that they're well matched to the natural statistics of contrast in the actual natural world. That so Lachlan actually went out with a camera and measured the distribution of contrast that the fly encounters, and the neurons are well adapted to that. Okay, that's a story, of course, about brightnesses and perceptual quantities. But Paul's point and the Paul Glimcher's point and the point of a number of other people in decision neuroscience is the same thing is true of decision variables in the brain, right? So one place that this has been seen, or argued to have been seen a lot, is famous work on risk attitudes. So there's a classic analysis of choice involving risk from Kahn and Tversky, prospect theory, right? Won the Nobel Prize. And one of the phenomena that it seeks to explain, or that they demonstrate, is that whether people are risk averse or risk seeking depends on whether you're talking about gains or losses. And in fact, you can take the same problem and describe it in terms of nominal gains or nominal losses, and people will switch between being risk averse and risk seeking on average. So that is to say that by sort of shifting the status quo, or the sort of baseline expectancy, the reference point they call it, you can actually shift people's risk attitude, and that arises in their model from what they call a value function, of utility function over losses and gains, that has this curved shape, which is, by the way, a lot like the curved shape you get in the fly as well. And a number of people have observed that perhaps, just as you could explain, sort of fly retinal responses in terms of the natural statistics of contrast in the world, perhaps you can understand uh, attitudes about wins and losses of different amounts that give rise to risk sensitivity in terms of the natural statistics of gains and losses relative to the status quo. And so the what is the status quo? Like, what do you mean correcting or shifting the distribution of outcomes towards? Then turns out to control the choices you make, like however sensitive you are. And in fact, there's been work on both sort of gain control, like scaling, but also shifts. A lot of contextual effects on this type of choice, these types of descriptive choices, where you literally give people a menu to choose from, turn out to reflect uh, relative valuations relative to the sort of prevailing past average reward. Looks just like, again, like R star. The same kind of equations again appear in these papers about risky choice. So it's as though people are tracking previous rewards and they're plugging that into prospect theory, and that tells you whether things look like gains or losses to them. And again, we can think of this as being another aspect of evaluating the environment, but now it's being evaluated not exactly for directly guiding choices, but for kind of assessing the mean around which to perhaps to efficiently code options in your brain. And in turn, you end up with sort of biases in your choices related to the uh, the coding that you end up adopting. Um, uh, okay, and again, a bunch of people have worked on variants of this model in this area, and I'm actually not one of them, but I thought I'd bring it up because it sort of relates to the broader theme of the sort of huge range of things that are affected by this sort of simple variable and simple logic. And that is what I had to talk about today. So I just want to say that average rewards and opportunity costs arise everywhere. So, famously in foraging, but also in many other choices that trade off the opportunity cost of time against other things. And also even in things that aren't really about intertemporal choice at all, but sort of efficient coding of other decision variables like amounts of reward that you might win or lose, and learning about them. And I think this also, in terms of this kind of thinking, I hope I've convinced you, has an interesting relationship with ideas about stress and mood, both healthy and disordered, and also dopamine. These might provide potential mechanisms for subserving these effects of average rewards on behavior. And conversely, the average reward and the sort of ideas around how it might affect many different types of behaviors might help to sort of rationalize or explain the diverse effects of these different things like stress and mood. I should end by saying I don't mean to say, of course, that these are all exactly the same thing. Right? Stress and mood are not the same, and I've sort of in a facile way identified them with a single kind of decision variable. I think in real life, there's going to be sort of fine-grained distinctions between timescales and aspects of environmental quality that have to do with good things and bad things, and many other aspects. And so there's sort of refinements to tease these things apart that we hope to pursue. But I think you could get pretty far with just the basic logic. I think it's sort of surprising how far it does. And so these are the people I worked with on the parts of this work that I was involved in. And thanks very much. I'm looking forward to chatting.
Oh, lovely. Thanks. That was excellent. Thank you, Nathaniel. I'm just going to invite our other co-organizers on screen as well. But yes, that was excellent. Thank you very much. So just to remind everyone that please use the Ask a Question button if you do have any questions. And we do have a question first from Alex Koselnik. Thank you for joining us, Alex. And Alex asks, so he says, the identification of mood with lost opportunity in foraging has difficulties. So say a rabbit is foraging and suddenly a fox chases it, but the rabbit escapes. Now, the rabbit thinks the environment has gone worse, so there's more predation probability, so there's worse mood. If this translates to foraging, it should stay longer in each patch because the worse environment means that there's less loss opportunity. So I think he's asking about the sort of the logic of the relationship between mood and loss opportunity in foraging.
Yeah, so let's see. So without completely understanding the details of that exact scenario, I think this relates actually sort of the thing I was trying to say at the end. One thing that's important there, I think, is there's a danger element as well as a reward element. And it's, I guess, true that I believe that the sort of classic work on the marginal value theorem type stuff folds both of those into the average reward. But Peter Dayan has done work also trying to take this apart. In the vigor circumstance, for instance, it's important to distinguish danger, which you have to act to avoid, from opportunities which you have to act to obtain. And so, in fact, isn't good enough to have a single variable. This is one example in which that's the case. And so you have to sort of, the questions, again, at least in the case of vigor, and I suspect probably in the choice case as well, potentially, need to account for in vigor, the inverted relationship between avoidance and successful action. So that's perhaps a way of thinking about that.
And I think Hannah has a follow-up question.
Yeah, you can hear me okay? Right. Yeah, yeah, it's I think related. So I found this very fascinating with the mood sort of reflecting your ability to adapt, and kind of the idea that the mood component can be used to track the slower changes in a way. I mean, sort of bridging things. But then I assume there's some natural amount of variability in how quickly things change, and does that actually correlate? Like, can we see a correlation with the ability to adapt to faster or slower environments better? Basically, right? Is there a rhythm that varies between individuals, and does that make us learn certain things faster or slower?
That's a good question. I don't specifically know between individuals. I mean, so let's see, a few things to say about that. In other learning contexts, there's been a lot of interest in within individual, how do we control the learning rate? So that, work by Tim Behrens and others on volatility says that we should figure out how fast the world's changing and we need to adjust our learning to track it. I don't think anyone sort of thought of that. The same context is presumably sort of true in foraging as well, and the world changes, the quality of the environment changes in different timescales from in different situations. Not only that, it's sort of multi time scale, right? It's not just faster or slower. It's also there's bushes depleting and also seasons, and also day-night cycles. And so again, I think it's more complicated, and I'm sure that real foraging theorists like Alex have thought through some of these scenarios, but there's a lot of room for multi-time scale kinds of inference and adjustable timescale inference in tracking this, and that again might be part of why I'm speaking of a sort of diverse set of systems here, or part of how they differ. There's also in the psychopathology setting, there is there's bipolar disorder, right? So there's work by Eran Eldar isn't exactly like this, but it's quite similar. So it has the idea that if you adjust your mood too rapidly in a model that's quite similar to the ones that I talked about, you end up with this sort of unstable dynamics that you get another type of disorder. Again, I wouldn't bet the details of that being exactly as I've described it, but it sort of has that feel.
Thank you.
And it looks like we have another question from the audience. So Johannes Algemissen asks or says, in reward-rich environments, opportunity costs of time are high, but each single reward foregone isn't actually too important for survival. So some people have suggested that in reward-rich environments, agents are more slothful and explore more. So for example, Jeff Beeler's idea of thrift. And can this be reconciled with the ARR or opportunity cost of time idea?
That's a good question. It does sound a little backwards from the way I've described things, and from the types of like the data I showed you from Josh Burke's lab. My guess is that the type of thing that Johannes is referring to has to do with diminishing marginal utility once you're getting towards satiety. Perhaps, and it may be that when the world is rich enough, you don't need to act so much because you've got plenty of calories, and so you're not really trying to optimize reward rate intake anymore, at least in terms of calories per second or something. So that might be why thirsty rats in Josh Burke's lab seem to modulate vigor positively with the opportunity cost of with the average reward, but and our model, which makes that assumption, predicts that. But I could certainly imagine situations where that wouldn't hold, basically because the marginal utility of reward is diminished.
Cool. Thank you. And I think maybe Dennis had a question now.
Yeah, first of all, thanks for your really inspiring talk. Yeah, I really have to say it's interesting to see like having a kind of very elegant one-dimensional signal to kind of track reward over time. I was just wondering, how would this play out in a like maybe more naturalistic case where you potentially have to like fulfill multiple needs, and there might be a need for tracking like multidimensional reward signals? Is this something that could be also fulfilled by this system, and how could that be like really biophysically implemented in the model of the extracellular dopamine? For
well, I think
example?
the extracellular dopamine certainly isn't the right substrate for that, right? So in fact, one of the things we talk about in that original paper that Niv talked about is this notion of generalized drive, right? So there are, going back to sort of instrumental conditioning psychology and the 60s and 70s, or even earlier, there's a notion that motivation has both specific components and generalized components, and there are and the thing that we think that this sort of univariate sort of scalar dopamine signal is doing is the generalized part of that it isn't selective to particular incentives. In fact, I tried to track down these experiments, and they were so old they weren't especially convincing or easy to find, but supposedly rats who were hungry will not just lever press for food faster, but lever press for water faster too, and run on wheels faster, and even things like you flood the cage and the animal will lever press faster because he's scared or something. So there's a sort of generalized aspect of drive that isn't tuned to particular incentives. The sort of modern version of that, I think, is known as general and specific Pavlovian instrumental transfer, if you've heard of that. And to get specific, to guide behavior towards specific outcomes, which is also important, also something the brain does, requires a sort of vector signal. I'm skeptical. There's a different discussion about whether dopamine is involved in this particular thing in the phasic part of dopamine, and that's maybe another conversation to have. I'm skeptical of that, but the brain has plenty of population codes for things, and you can certainly have codes for different outcomes as well, and you can guide behavior towards the ones you need.
I think on a sort of related note, I have a question about perhaps your thoughts on the relationship between. So you described this this work which found a relationship between reward rate, dopamine, and movement. And I was wondering if you had perhaps more thoughts about learning of new reward rates in new environments, right? And the interactions perhaps between phasic and tonic, however we might want to define that, dopamine in completely sort of novel contexts. Because I think also this kind of relates to a secondary question I had, which was about the design of a lot of foraging tasks in humans and also in rodents, which tend to present, for example, environmental richness in blocks, right? Like you have short travels and long travels in blocks, and these are very kind of, they're experienced over and over again. And so I guess in a very broad sense, what I'm asking about is like dynamic or changing or completely new environments, what kind of role dopamine might be able to play over different timescales. Sorry, it's a very broad question, but I think maybe perhaps you know what I'm sort of getting at here.
Yeah, let's see. So there's a bunch to say about that. I mean, I think that you're right that the marginal value theorem is a sort of static equation that describes well-earned optimal behavior, like when the animal knows what he's doing in the steady state, what relationship should obtain for his optimal choices. And yet it's also kind of obvious, and I'm not the person who invented this, so this goes back to McNamara or somebody at least, and again Alex I think has had some involvement in this as well over the years. It has an obvious kind of learning rule associated with it, right? If you're tracking the average reward by something like a running average, and then you're adjusting your behavior with respect to that, then you're going to do things that are relatively better than you're doing before, and then your average reward is going to go up, and you're going to, you're going to get more picky as you figure out what to do, or if you happen to overestimate, you're going to get less picky as you figure out you're not doing as well as you should. So you can sort of turn the marginal value theorem into a choice rule with a learning component just by learning the terms of it, in particular that average reward, and that's the type of model that we fit to the learning experiments I talked about. So that's, I guess, one thing to say. And again, that learning rule contrasts to the type of learning rule that we usually associate with dopamine in the sort of choice scenario, right? Where you're using the prediction error to learn about, the value of this lever or that lever to update individual options. This is a learning rule in which you update, you just, average received rewards, let's say, or average dopamine responses to track the sort of overall density of rewards, not the density of rewards, just sort of individual options. And one thing that's interesting about that, actually, and this relates to this discussion with Josh Burke about the interpretation of his data, and maybe also to your point about novel environments and so on, is that, what dopamine sort of famously does as you learn in the world is that responses transfer, right? So the Schultz experiment showed the dopamines respond to unexpected rewards, but as the animal learns that earlier signals predict those rewards, the response doesn't disappear. It moves from the reward to the stimulus, or to an even earlier stimulus that predicts that stimulus, right? So dopamine, the prediction error, has this predictive quality to it that emerges through learning. That's interesting from the perspective of the foraging theory, because as one of Josh's points about his data is that the tonic, the sort of background dopamine signal that seems to relate to vigor and so on, looks to be anticipatory in these sort of well-trained rats rather than responsive. So it seems to lead rewards and respond to other task events, or even anticipate task events, instead of sort of tracking actually received rewards. And I think that makes sense from the perspective of what dopamine does, right? If you average dopamine, it turns out mathematically, because responses only move, they don't disappear, that you still get the average reward, but you get the average reward from this sort of signal that has this sort of predictive property that's acquired through learning. And so so you're sort of layering two types of learning, as it were. One about how well can we predict rewards, and one about how often a reward's coming. One lives sort of on top of the other on this model. I think there's a lot of interesting interactions we haven't completely, to be honest, worked through in that setting, but maybe that's the kind of thing you were getting at.
So I'm maybe a little naive in this, because I work with flies, and so it's a little bit about this sort of, I'm trying to wrap my head around these learning rules, and then the transitioning between different rules, etc. So what I'm trying to understand is, are all these findings, and like, do the models mainly hold then in the conditions where you have fully trained animals, where basically, like, I'm trying to understand, how do I balance learning even about the structure that the environment has, right? Like, they assume there's specific components that change in the environment, and there's a clear structure. And so once I have learned this, then the transitions are easy. But like, would I learn in the same way if I was learning everything at once, for instance?
Yeah. So I think that's an incredibly tricky problem when you take it to the extreme, and maybe that's what you're intending to do. So let's see. So if you think about, I don't know anything about flies, so I'm not even about flies. Let's think about putting a rat in a box, right?
It's not important. It's just that I can't train them for a long time. So that's where I'm coming from, right? Like,
So let's imagine we put a rat in a box, right? And the rat has to learn to lever press for food. Or this lever is better than that lever, or something. There's a whole bunch of stuff the animal has to figure out before he gets to the point that he's got the sort of actions and outcomes and stuff that our models refer to, right? He just know the lever is a thing you should care about, and that the lever delivers food over here, and and he has to go over there to get it. So, and he should pay attention to that and not go groom in the corner. And there's just like a huge amount of attentional and sort of representational and sort of like sort of dimensional attention and so on that sort of has to happen, and sort of set learning. I don't know what to call it. Right? There's a ton of different things that are sort of going on when the animal first acquires a task, and I think it's very challenging to that's a little too abstract and sort of to really nail with these sort of simple models. So what we've tended to do in my lab, and I think many people in sort of decision neuroscience have done this, is study learning in the steady state, in the sense of have some task that's constantly changing, so that once you figure out kind of the initial stuff of just getting oriented, then you still got to keep learning for the rest of time, because it's always reversing or it's always drifting or something, and you've got to this lever's better than that lever's better than this lever's better, and so that sort of assumes away the problem that you're talking about, because that's a hard problem. My colleague Jonathan Pillow and some of his students have tried to work on the more general problem of sort of de novo learning, and I've been working on it with them and with Lana Witten and Carlos Brody, but and they've had some success fitting models to data from day one of a mouse learning to do some task, and they have a project called Sidetrack that you can read about and download, and I think that gets it bits of that, but it's still very kind of stripped down or projected onto the things that we're sort of measuring and caring about, but presumably the animal's real experience is much more complicated than that, and we don't have an account for that.
I think we have time for one last question. Yes, we have a question in the chat box, and this is from Charlotte Rocher. And she says, thanks for the interesting talk. Memories can be flavored a lot by emotions, not only the emotions that we had at that time, but also our sort of current emotions. Do you know if this is something that has been studied in a foraging context, where we can see rewards more easily?
So I'm not, so let's, I'm trying to, there seem to be a lot of pieces to that. I'm trying to understand what she has in mind. I've certainly been interested kind of in other work in emotional memory, work with Deborah Talmy and others. It is certainly true that memory is modulated by emotion, presumably in part because it's important to remember things that are, the key incentives in the world. And I guess it's also true that learning things like how rewarding is your environment, or how rewarding is this particular lever, is in some sense emotional learning. It's sort of evaluative learning, and I guess it's also memory in the sense that it's forming a record of past events. I'm not sure I quite understand how to put all those things together to say that emotion further modulates that learning as sort of I think of that learning as sort of being emotion in this particular case, different from the case where you're looking at a bunch of pictures and some of them are car wrecks or taboos or something. Then you have extra sort of memory for the emotional items. In the foraging context, they're all emotional items. That's what you're trying to learn, the valuable stuff, and I think that's sort of how it is. So I guess I'm not sure I know what more to say than that.
So yeah, I think we should probably wrap things up now, since we're at 20 past. Nathaniel, thank you so much again for your really interesting talk and answering all of our questions. We really enjoyed having you as part of our seminar series.
Thank you so much.
I believe our next episode should be in a couple of weeks, which we'll be advertising on Twitter and email and so on. But yeah, thank you very much. And yeah, hopefully see everyone here soon again.
Yeah, thanks. Thank you everyone for joining.
Thanks.
Thank you.